Good morning. On behalf of the Chairperson, Department of Physics, I, Gulsheen Ahuja, extend a warm welcome to respected Dr. A.K. Mohanty, Secretary, Department of Atomic Energy and Chairman, Atomic Energy Commission, to the Honorable Vice Chancellor, Professor Renu Vait, to all the distinguished guests, colleagues, and dear students. Before we start today's program, you're all requested on behalf to stand up for the PU Department of Physics. I, Gulsheen Ahuja, extend a warm welcome to respected Dr. A.K. Mohanty, Secretary, Department of Atomic Energy and Chairman, Atomic Energy Commission, to the Honorable Vice Chancellor, Professor Renu Vait, to all the distinguished guests, colleagues, and dear students. Before we start today's program, you're all requested on behalf to stand up for the PU Department of Physics. I, Gulsheen Ahuja, respected Dr. A.K. Mohanty, Secretary, Department of Atomic
रोज पढ़ाकर सही गलत की समझ बढ़ाता तेरी जय शंख बजाए बखरी तेरी शोहरत सदा सदा रहे
Thank you. Now I request Dr. Mohanty, Professor Renu Vait, Professor S.K. Tripathi, Chairperson, Department of Physics, Professor P.K. Ahluwalia, President, Indian Association of Physics Teachers, and Professor Arun Grover, former Vice Chancellor of Punjab University, to please come forward on the stage for lamp lighting and to take the seats on the stage. I request Professor Tripathi to please present flowers to Dr. Mohanty and to Professor Renuve. I invite Alicia and Arman to please present flowers to Professor Aluwali and Professor Grover. Beginning today's program, now I request Professor Tripathi to please present the welcome address.
Good morning to all of you. Dear Dr. A.K. Mohanty, Chairman Atomic Energy Commission and Secretary, Department of Atomic Energy, our worthy Vice Chancellor, Dr. Renuji, Dr. P.K. Aluwalia, Dr. A.K. Grover, and other esteemed guests and colleagues. Today I feel honored and privileged on behalf of the Department of Physics to get the opportunity to welcome Dr. A.K. Mohanty ji, Chairman Atomic Energy Commission and Secretary Department of Atomic Energy, to deliver the Professor H.S. Hans Birth Centenary Lecture on Atoms in the Service of the Nation. About the Physics Department, though all of you are knowing, but I should give some brief introduction. The Department of Physics was established at Lahore in 1934. Then it moved to Delhi after the partition for some time, and then to Government College, Hoshiarpur, Punjab. Subsequently, the department was shifted to Chandigarh in 1958. The department had previously received grants under the different funding agencies like UGC COSIP, that is College Science Improvement Program, from 1977 to 83, SAP, Special Assistance Program from 1980 to 88, and Committee of Strengthening of Infrastructure in Science and Technology, COSIST, from 1984 to 91. Since 1988, it has been accorded the status of a Center of Advanced Study, CAS, by University Grants Commission, with three major thrust areas: particle physics, nuclear physics, and solid state physics. A unique achievement. At present, the department has the strength of 20 faculty members, 30 assisting staff, and 2 daily wage staff, apart from several postdoctoral fellows under various funding schemes, as well as project scientists, investigators. There are about 108 research students and 437 BSc students honors school physics, MSc honors school physics, BSc honors school physics specialization in electronics, and MSc honors school specialization in electronics students on the rules of the department. About 150 BSc honors school students of other departments study physics subjects as a generic elective courses. The faculty members of our department have honored with Meghnad Sahai Award, Goel Prize, Kurukshetra University Award, Sir C.V. Raman Award, Hari Om Trust Award, S.N. Sattamurthy Young Scientist Award, D.I. Young Scientist Award, Himachal Scientist of the Year Award 2011, Chinese Academy of Sciences President's International Fellowship, Mercator Professorship, Homi Bhabha Fellowship, Emeritus Scientistship, Ramanna Fellowship, Raman Fellowship. They have been elected for Indian Academy of Sciences Fellowship, Juliet Curie Fellowship, Alexander von Humboldt Fellowship, German Research Society DFG Fellowship, BMFT, that is Ministry of Research and Technology of Germany Fellows, UNESCO, IAEA Fellowship, W.E. Harris Fellowship, Henrik Hart Foundation Fellowship, Fulbright Fellowship, Commonwealth Fellowship, IN2P3 CNRS Fellowship, France, Third World Academy of Sciences Fellowships, and UGC National Lecture Fellowship Awards. Our faculty had also served, is serving at various administrative positions such as Vice Chancellor of Punjab University and other universities. The department is having research collaborations with different institutions like Royal Military College of Canada, University of Notre Dame, USA, BNL USA, Fermilab USA, CERN Geneva, Bonn University Germany, University of Paris, Würzburg, Munich and Berlin in Germany, Chemistry Department, City College of New York, Keck, Japan, Chinese Academy of Sciences, Shanghai, China, ICTP Trist, University of Illinois, USA, BNL USA, Max Planck Institute, Germany, University of Leipzig, Germany, Subtechnet, France, Institute for Theoretical Physics, Tübingen, Germany, Institute of Nuclear Studies, Warsaw University, Poland, University of Milano, Italy, JL University, Germany, JW Goethe University, Frankfurt, Germany, Institute of Nuclear Physics, Strasbourg, and many others. In India, the university have collaborations in BRC Mumbai, IUSC New Delhi, IIT Kanpur, Delhi University Delhi, Mumbai University Mumbai, IIT Chennai, IOP Bhubaneswar, Himachal Pradesh University Shimla, TBRL Chandigarh, PGI MER Chandigarh, CSIO Chandigarh, Jammu University Jammu. The department has MOU with several institutes like IUSC New Delhi for joint faculty appointment and to various academic exchange programs for accelerated based research. UGC had sanctioned 3 crores under CAS 5 fifth phase grant under improvement of infrastructural facilities of the physics department. Funds of rupees 3.5 crores for infrastructure development have been sanctioned by the Department of Science and Technology under fifth program to upgrade teaching and research facilities. There are several achievements by the faculty members. They have been honored with, already I have discussed different Meghna Sai Award, Goel Prize, Homi Baba, Ramanna Fellowships, S.N. Satyamurthy Young Scientist Award, D.A. Young Scientist Award. They have been elected for Indian Academy of Sciences Fellowship and many other funding agencies. So, thank you very much. On behalf of the department, we welcome to all of you. Thank you very much.
Thank you, Professor Tripathi. Now I request Honorable Vice Chancellor to please honor Dr. A.K. Mohanty by presenting the shawl. Today we have gathered here for Professor H.S. Hunt's Birth Centenary Memorial Lecture. Professor Hunt was an eminent nuclear physicist who was head of this department from 1967 to 1979. We are happy to have among us his family. We have Mr. Vikram Hunt, his son. Now I invite Mr. Vikram Hunt to please come on the stage and share his thoughts.
Hello. Good morning, everybody. Thank you, Dr. Mohanty, for being here with us. It is indeed a great pleasure and honor to have you amongst us today, and we appreciate your efforts, especially because you could take out this time, and I'm sure you're surrounded by so many national matters that this was worth the wait. That's all I can say. Our family, Mrs. Hans, myself, and Simi here, my wife, would like to take this moment of opportunity and express our personal gratitude to Dr. Mohanty. Simi, can you please do the honors? In the given 3 minutes, I would like to say as many thank yous as possible. Uh, Briefly, to start with, Mrs. Hans is today 94 and could not be here physically. But she's watching this event on the YouTube and sitting at home live. And she may not exactly know what Higgins did in physics, but she surely knows what uh, uh, Manjeet Kaur did, and she surely knows what Suman Bala did, and she surely knows what Kaya does in physics, and her blessings are with all of us because she considers this as her family. We are grateful to all of you on the stage here for supporting and making this happen. Thanks, Dr. Renu Vij, for giving a break to the selection committee and being with us. I know your busy schedule and I appreciate this. Thanks to the team in the physics department who brought forward the energy and the passion to make the results as we see in front of us today to make this happen. I would name a few, Dr. Bera is there, Dr. Vipin Bhatnagar, Dr. Ashok, Dr. Devinder Mehta. I can't see Dr. Devinder Mehta. Yeah. Dr. Vimal, Dr. Sehajpal, Dr. Navdeep Goel, and of course Dr. Aluwalia from IIT. He has been supporting this for the last 2 years and he has been inspiring me that we must do this in a bigger way, of course, in the times to come. And I must thank the students who made this beautiful Rangoli outside. I do not know the names, but I must thank the students who made this Rangoli outside. I got a picture of this last evening and I showed it to my mother and she was delighted about it. Special thanks to Dr. Grover, our mentor, Dr. Grover, my friend, who always led with his persistence and insistence and assured us that this magic will happen. There was a time when I had given up hope and I said, whenever it happens, it happens. But he kept on egging me on, he kept on egging the department on that Dr. Mohanty will surely come and Dr. Mohanty can validate it. On this side, there are some people who were associates of Dr. Hans and who have known him since he landed here in 1965. He landed here with his dream, his vision, and this wristwatch that I am wearing today. On the other side, I have someone here who was working with Dr. Hans on a research paper just 1 week before he left us. And that research paper got accepted a couple of months later. That research paper is dedicated to him by whoever was working with him. That was Dr. Ashok Bhatti was working with him at that time. This was the trajectory of his life, work, and the timeline in this campus. I must share a small a dining table that we have at our house. I'm sorry, I'll finish in 3 minutes. On this dining table, there has been much more science discussion that could ever happen in the lifetime of a normal human being. The few names that I recall at the top of my mind at this moment, Dr. Bamba, his daughter, is here with me today. Dr. Pyara Singh Gill, his teacher, his mentor. Dr. Reis Ahmed, Raja Ramanna, and Vikas Sinha. I remember these names distinctly because these conversations were long, sometimes inconclusive, and left with a promise that yes, we must do something and make sure that science in this country moves a couple of notches ahead. These are memories that are very vivid and will not go away soon. This is not the first memorial lecture. Let me assure you, this is not the last one. Dr. Grover, please. I'm ready for more. The family is committed to work with the Physics Department, Punjab University and IAPT for building up the scientific temper in the ecosystem, in the community and students at large. We stand by all of you with this promise today. Three things that Dr. Hans would often say to me: figure out infinity whenever you're getting really bored. Nature has a very good reason for everything, sometimes beyond scientific logic. Given your coordinates of time, space, energy and money, what is the maximum you can achieve? Please look up www.hshans.com for more information about the research work, about the movie Janvi Falke made on the cyclotron, and many more things. And Janvi Falke is the Director Presently of the Bangalore Science Gallery. Thanks and wish you all a wonderful day ahead. Thank you so much.
Thank you. Now I request Honorable Vice Chancellor of Professor Renuwit to please come forward and say a few words.
Dignitaries on the dais, in the audience, faculty and students. Right now, there is a meeting going on in the VC office, and I told Vikram that I'll be meeting Dr. Mohanty during lunch, but he insisted that I have to be here. And I have known Vikram almost all my life. Not only he is my senior from Punjab Engineering College, but when he was working in Wipro, my husband Sandeep was also working with him, and the dining table that he was just mentioning to, we have also been around that dining table many times. And when he said I have to break the, give a break in between for these elections and come here for 15 minutes at least, that's why he was referring to 3 minutes again and again. So I welcome Dr. Mohanty for coming here for Professor H.S. Hans Memorial Lecture to the Physics Department of Punjab University. And the department has given me some, contributions of Dr. Hans that was made during his lifetime, and I will just like to read them for you. So we all know that Professor Dr. Hans was a distinguished nuclear and accelerator physicist of the country and the second chairperson of this department. And the memorial lecture is being delivered by none other than Chairman of Atomic Energy Commission and Secretary, Department of Atomic Energy, Government of India. Professor Hans, who joined as professor and head of Department of Physics in 1967, was instrumental in setting up the cyclotron accelerator lab at Department of Physics. He gave a modern look to the department and started research division in experimental physics like accelerator-based nuclear physics, condensed matter physics, and high energy physics. He recruited several young physicists during his tenure. Later, all of them had contributed in shaping the department. After setting up the cyclotron laboratory, he established a group of perturbed angular correlation in the physics department. He realized the accelerator-based research within university system and wrote the project proposal for a 15 UD accelerator. Later, with the support of the government, Nuclear Science Center, presently known as Inter-University Accelerator Center, was established at New Delhi. throughout his life, he remained active in research at Department of Physics, Punjab University, and contributed in all the aspects of the department. As Vikram just mentioned, that he published his last paper at the age of 92, and he was associated with the Indian Association of Physics Teachers and Indian Physics Association throughout his life, and both these associations had honored him at several occasions. Punjab University also honored him with the lifetime emeritus professor position. Today, Department of Physics has diversified research in various branches of physics, notably in nuclear physics, high energy physics, condensed matter physics, and astrophysics. Students of this department are serving in various institutions throughout the country. The cyclotron established by Professor Hans is still being used for research by students. I wish all the students of this department the very best and hope they will follow his dedication to achieve their dreams in life. And I'm sure Dr. Mahanti, who is here, will also inspire the students as well as the faculty to take a career in atomic energy sector of this country. Personally, I had the opportunity to visit Homi Bhabha National Institute, which is a deemed university established by Department of Atomic Energy. And Homi Bhabha National Institute has 10 constituent centers for award of master's and PhD degrees. So I visited the Homi Bhabha National Institute as a member of the NAC Accreditation Committee in 2015, and it was a very big committee consisting of 15 to 20 members, because Homi Bhabha National Institute has 10 constituent centers, and the team was divided into, different sub-teams, and some team members stayed in Bombay for evaluation of BARC and Tata Memorial Centers. Some team members went to Kolkata for Saha Institute of Nuclear Physics and Variable Energy Cyclotron Center. Some went to Bhubaneswar. I had the opportunity to go to Raja Ramanna Center for Advanced Technology, Indore. And I can tell you that during our visits, we were shown the various complex and elaborate systems which have been designed and developed at various centers associated with Homi Bhabha National Institute. And it was amazing to see the kind of complex systems that have been designed and developed in India by these centers under Department of Atomic Energy. So this concept of Make in India has been with the centers of Department of Atomic Energy since their inception. So they have been doing this since their inception, and that's why the Ministry of Human Resource and Development at that time approved that HBNI be recognized as a deemed university so that they can award their own degrees to the education programs that are going on at the different centers. And today, although we are as a nation taking conscious steps to manufacture many international brands in India, but our Department of Atomic Energy and various centers under it have been doing this work for the nation for a very long time, since the early 60s. And I'm sure the interaction with Dr. Mahanti will be beneficial for all of you and will motivate you to work with dedication in your life. Thank you. Wish you all the best.
Thank you, ma'am. Today, to deliver the Professor H.S. Hans Birth Centenary Memorial Lecture, we have among us Dr. A.K. Mahanti, who is a well-known nuclear physicist. Presently, he is Secretary, Department of Atomic Energy and Chairman of Atomic Energy Commission. Before his present position, he has held several prominent positions like Director of Bhabha Atomic Research Center, Director of Saha Institute of Nuclear Physics, and Director of Physics Group, BARC. He served as Secretary and Member Secretary of BRNS Basic Science Committee, the General Secretary of India Physics Association, and later on its President. He has been the India CMS spokesperson of CMS experiment at CERN. He is a Fellow of National Academy of Sciences and of Indian National Academy of Engineering. During his illustrious career, he has been recipient of several awards and recognitions like Young Scientist Award of Indian Physical Society, Young Physicist Award by INSA, and D.A. Homi Bhabha Science and Technology Award. During the past 4 decades, Dr. Mohanty has worked in several areas of nuclear physics, covering collision energy from sub-Coulomb barrier to relativistic regime. Today, he will speak on the topic Atoms in the Service of Nation, highlighting contributions of nuclear technology in achieving energy security, health security, food and water security, and national security. With this, now I invite Dr. Mohanty to please come forward and deliver the talk.
Wait a minute. Okay. जब इसका अप डाउन करने के लिए Good morning to all of you. Honorable Vice Chancellor, who just left it, so nice of her that she could be here. Professor Grover, who has been instrumental bringing me here. Professor Aluwalia, Professor Tripathi, Mrs. and Mr. Hans, my senior colleagues from Punjab University Physics Department, and my dear students. I have been very fortunate being selected to give this memorial lectures. Professor Hans, it is one of the prestigious lecture of this department. And I'm on the other hand, I'm sorry that it took me 1 year to come here. So this is my first apology. And second apology, that I have been coming to this university many times. Last being 2015-16, when I gave a talk to some of the students as a part of IFPT on that Higgs boson, because that is the time I was just continuing as a spokesperson of CMS experiment. They detected Higgs boson. But then I never went down. Today morning where I went, visited a cyclotron which is 88 years old and since working. And it came to this department when it was mid-30s, and Professor Hans adopted it. It is the adopted son of Professor Hans. And you know, anything adopting is more difficult than building it. And he did a lot of things. His colleagues, Professor Govil is not here, other colleagues, they modified the magnets, they modified the vacuum systems, everything. That's why it is alive today. And in my opinion, it is a pilgrimage for me, pilgrimage of the cyclotrons, of Indian cyclotrons. And one such cyclotron, Professor Sahav also started to make it indigenously in 50s. I know how difficult it was. Professor B.D. Nag Chaudhary, with his help, he did it. But it was so difficult because you need fundings, and that is the time India has got independence very recently. Funding situation was not that good. Although everybody wanted the cyclotron should be made, but it was difficult. So finally, he thought he should go to the parliament and fight it. And he fought the election and got elected 1952. He is the first scientist to become the member of parliament. And you know, one of the parliament debate, I have heard it in a newspaper, some writings. The great Ganesh Mablankar was the Lok Sabha Speaker of the first Constituent Assembly. Honorable Nehru was the Prime Minister in the Treasury bench. And there are stalwarts and parliamentarians in other sides like Hiren Mukherjee, Shyam Prasad Mukherjee, Madan Mohan Malviya, Ashok Mehta, and people like that, stalwarts. Then a young fellow got up and told suddenly in the parliament, if government of India wants to give me 5 crores, I will change the scenario of this country, making it a hub of science and technology. He was none other than Meghnad Saha. But today I wonder whether we will be so fortunate to see in the parliamentary democracy such a debate coming. Probably not. And this is the difficulty what we have today at that time. But he got some money with the Tata Trust. Similarly, Department of Atomic Energy also gave some money to Professor Hans. They could rehabilitate this child which was brought from Rochester. But unfortunately, no other cyclotron of that era is working except this one. And I am very proud of it. And I am rightly so that I am giving this memorial lecture. And I was talking to Professor Gabbar little early. I feel jealous that Homi Jahangir Bhabha, when he started atomic energy, I was not knowing that all the talents of this department he has stolen to the atomic energy. Starting from Professor Brahma Prakash and Professor Gabbar himself, and then Professor Ajoy Sood, who is the PSA, everybody. Whomever is the stalwart, they are from physics department of the Punjab University. And we are filled up from you, you students, you will be the one day pillars of the atomic energy, I am sure. Now coming to my topic, I have chosen a very simple topic. Atom for the nation. It has started from the Professor Hans itself. He has started, the accelerator itself is an example of atoms for science, and it has gone long way. And in his book, Nuclear Physics, Theory and Experiment, somewhere is mentioned, the nuclear fission is one of the greatest discovery of the mankind, because the God has stored all the energy in the atom. You can take it out the way you want it. You can split it, you can join it, or you can take it in forms of radiation. So all energy can come from the atom. But the strength of this atom was not realized until 1945. Until it was misused. Misused in the sense that you see this photograph. Oppenheimer, you must have heard about him. He was the leader of the Manhattan projects, and he was asked to develop the atomic bomb. And before it was dropped in Nagasaki and Hiroshima in 1945 August, in July, he did this test. This is called Trinity test. It is an underground test. And when this happens, he is a great scientist, and also he is a great scholar of the Sanskrit scholar. He has read entire Gita, 11th stanza of 12th, 11th chapter of the 12th stanza in Gita. Seeing this, he told, Divisurya Sahasrasa Bhavat Juge Pravatispitam. That means, this is what he told, if 1,000 suns spread in the sky at once, the glory you will see will be the mighty one of this picture. And he told, now I become the death, the destroyer of the world. And a couple of months later, the bomb was dropped in Nagasaki and Hiroshima. Then you all know what happened. It was, although as a scientific discovery, it was appreciated by everybody, but it was condemned because the energy was used for harmful purpose of the mankind. Then came in 1953, US President Eisenhower addressed the United Nations of General Assembly in New York and delivered what became known as the Atom for Peace. That is a famous speech. Last year it completed 70 years of that speech in International Atomic Energy Agency. I was also there, we celebrated. And he lauded the civilian nuclear application in agriculture, medicine, and power generation. He proposed the establishment of an International Atomic Energy Agency that would promote the peaceful uses of nuclear energy for the benefit of the mankind. This is what my talk all about, because after Bhabha returning to the India in 1939, and he could not go to Cambridge because of the World War, he started everything in India. In 1945, he came to Bangalore. He started, joined Indian Institute of Science, Bangalore, but there later on he started his own institute what is the mini firm of Tata Institute of Fundamental Research in 45, and very soon it shifted to Mumbai, Kenilworth, that it became the headquarters, and from Kenilworth he went to another place called Old Yacht Club. It was the club of British India. Today it is a heritage building next to the Hotel Taj, and he started Tata Institute briefly in that institute, and then finally it shifted where it is today in the Colaba. On the other hand, in 1954, he thought that when Tata Institute of Fundamental Research should do basic research, fundamental research, it should be translated into the technology, and the benefit should be reach to the people of India. So he started atomic energy establishment at Trombay, which is around 30 kilometers away. It is a South Bombay, and Trombay atomic establishment, it is the eastern part of the Mumbai. Today what is known as Bhabha Atomic Research Center. It started in 1954, and today we are completing 70 years. And he started with one reactors, as Professor Hans started with the accelerator here. He started nuclear reactors, because you can take out the energy by splitting it, putting into a reactor, nuclear fission, or take some subatomic particle like proton, give energy and accelerate it to do something, some miracle to do, which I will come to later part. So these are the two pillars to cultivate energy from the atoms, and these are the, just I told them, I will just go through. So since then, since Bhabha started Bhabha Atomic Research Center, our motivation has been to harness the enormous amount of energy from the tiny atom in a controlled way for the service of the mankind. If you don't control it, it is nothing but an uncontrolled chain reaction, nothing but an atomic bomb, like a fire. If you don't control the fire, it can ruin you, but you control, then it will become a factor for the mankind. It is similarly same thing. Use the energy the way you want it. So today, when I say atomic power, it generally refers to the nuclear energy released by fission, nuclear fission, all of you know, or maybe fusion. It is not technology yet, one day it will come, which is primarily consumed for electricity production, green energy production. However, atomic power can also be realized through nuclear radiations like alpha, beta and gamma rays, and through subatomic particles like electrons, protons and neutrons. These kinds of harnessing atomic power has now matured into technology, and all of these subatomic particles or atoms itself, probably they are the friends of the society today. I will be telling in a couple of slides. So therefore, the mission of the Department of Atomic Energy has been to achieve for the country energy security. When I say energy security, it would mean electricity generation, power production, like renewable energy. In that sense, it will be contributing a lot, mitigating global warming. National security, we have to be secured from others. Health and food security, we have to feed our people, we have to remain healthy. So it would mean radiopharmaceutical, nuclear medicine, nuclear agriculture, food preservation, etc. Radiation technology leading to economic and societal benefits for better quality of life. In addition to that, we have to do basic, applied and transnational research using subatomic particles. In addition to that, the mission of the department has been to carry out collaborative research with universities and academic institutes in all fields, including physics, chemistry, biology, mathematics, material science, engineering, etc., either directly or through various funding agencies like BRNS, NBSM, National Board of Higher Mathematics, UGC DAE, Consortium, to name a few. So if you look our family today, we are quite big. We started in a modest way. Tata Institute started in 1945, where Professor Grover was the alumni. This is what Kenilworth. Moved to Old Yacht Club. Bhabha got it from the British India, and today it is the headquarter of atomic energy, where department ICU. Tata Institute also here briefly, but then it shifted to the new campus. This is where Prime Minister Nehru and Bhabha, they are setting up Bhabha Atomic Research Center. There is a reactor called Apsara, which I will be showing later. This is what started in BRC, and today, in the past also, it started with a reactor called Apsara. Then it went to Cyrus reactor, Dhua reactor, and in between we have several mini reactors like Purnima, Jarlina, Tamini. So I should say Department of Atomic Energy. If this place is pilgrimage of cyclotron, probably Department of Atomic Energy is a pilgrimage of reactors. Unfortunately, Baba died in a plane crash in 1966, and after that, Mrs. Gandhi renamed that establishment, which was Atomic Energy Establishment at Trombay, as Baba Atomic Research Center. The lady in the photograph people see is the mother of Homi Baba. Madam Gandhi is consoling her. This is the two extreme end of our establishment. One is TFR, which is the right hand side, the way it looks today, and another is BRC. Step has changed, they have become modern, but it started at a very modest beginning. And department today, we have 30 departments, 17 are units, like you will have, we work in power sectors, responsible producing nuclear power, NPCIL, Nuclear Power Corporation of India, and Bhavini, these are looking after the power sector. We have R&D sectors, only research and development. Baba Atomic Research Center is one of them, premier one. Indira Gandhi Center of Atomic Research, Kalpakam. Rajaramana Center of Advanced Technology, Indore. Variable Energy Cyclotron Center, Kolkata. Atomic Mineral Division and Education and Exploration, Hyderabad. GCNP, Bahadurgarh. These are the R&D centers. We have industry and mineral sector. We mine our own fuel and make it our own fuel for the reactor. That is Nuclear Fuel Corporation of Hyderabad. Largest unit globally in one scar under one umbrella. We use heavy water for our own reactors. Heavy water board. We are the largest producer of the heavy water in the country globally today. We market radioisotope, Board of Radiation and Isotope Technology, BRIT. It is in Navi Mumbai. We have mines for our own fuel, Uranium Corporation of India Limited at Jadugoda, Electronic Corporation of India Limited, Hyderabad. Voting machine, what you are seeing today, come from this ECIL. All voting machine. Today we are serving the nation, providing the self-secured voting machine for electronic, whatever election or anybody pressing a button today, made by that machine in ECIL. Indian rare earth elements, which probably I will not be covering today. Another strategic sector, we own it. Then we come to aided institute or autonomous body. Most important, they are the hub of the fundamental research, like Tata Institute of Fundamental Research, Saha Institute of Nuclear Physics, Tata Memorial Center. This is our health sector. We are primarily the largest taking care of the cancer patient today in India. This is at Tata Memorial, and it is within the Department of Atomic Energy. In fact, in some last couple of days, I was going to attending a function in Tata Memorial Center in Utrecht, Mumbai. They are trying to introduce, saying that Tata Memorial Center, we have now 11 of them, various parts of the country. 2 are in Punjab. Professor Ashish is sitting here, he is looking after that. And they say that Tata Memorial Center belongs to Department of Atomic Energy. But I say, in Department of Atomic Energy, they feel proud, but I also feel proud saying the Department of Atomic Energy owns Tata Memorial Center. That is the identity of each other. So like this, we are now 30, and jokingly I tell everybody, as far as science, technology, healthcare, everything is produced, we are a mini India. If you scale it up, it will become India itself. So what is not happening in Department of Energy, it is not happening elsewhere. Now I give a selected examples to justify what I told. Very quickly I will give. Let me come to the energy security. This is a novel which got a prize in 2014, Elizabeth Colbert. It talks about 6 extinction. And you know, when the universe is created after Big Bang, I do not know what is the age of this, but people said it is 5 billion years back, and it will survive another 5 billion years. And definitely, in this evolution, there are 5 extinction have happened naturally because of natural phenomena. Dinosaurs, you don't see them today; it is extincted. So, like this, the authors argues here, 5 extinction has happened for last 5 billion years, and definitely one more will happen. That is the 6th extinction that will be created by human beings. And you know why she is telling that? Our own activity, because the way temperature of the earth is rising, if you don't control it, by end of this century, it will be 4 degrees Celsius with respect to the average temperature of the pre-industrial era. And that's why we are whole concern. We want to carbon free. It should be globally carbon free, and we promise that by 2070 we should be free from any type of carbon emission. Again, it is a promise unless we work it, because it was not an unknown thing. You know, Professor Manabe, who got Nobel Prize in 2013, he has demonstrated this as early as in 60. Two important phenomena in 60s that happened. Peter Higgs proposed that there is a particle which is giving mass to everybody, God particle, which I discovered later on. And he also told the rise in the carbon dioxide is proportional to the rise of the temperature of the global temperature. And nobody believed it, or nobody did the experiment to find out the Higgs boson. Lot of people did the experiment. It took 50 years, and CERN is an example, because it was doable. But to prove that global warming will happen, temperature will rise, probably nobody could have done the experiment. But the people at large did the experiment. Today we know the temperature is rising. And if you don't control it today, there is a cartoon to show that this will be a picture after a couple of years. It is a 2 times. It was assumed in 2020, Gateway of India will look like this. It will full of water. Thank God that it has not happened, but going to happen very soon if you don't do anything. If you don't do anything, our motto today has been Vasudhaiva Kutumbakam. One earth, one nation, one fusion. One earth, one nation, one vision, one dream. And it is very easy to see that. Don't do anything. Burn the coal, live the way we live it. Automatically, temperature will rise, glacier will melt, and everything will merge with water like this. So you will also have one earth, one globe, one earth, and no future. And it is easy to achieve it. But if you want to divert it, if man can destroy it, I always say man can prevent it also. And prevention is only possible harvesting energy, all possible ways where there is no carbon dioxide. You can take from wind, you can take from solar, and also you can take from any other, but probably they will not be surviving, they will not be giving you the sustainable development if you require. You need a supply which will give you 24/7 and in any quantity, and that is only the nuclear energy. And nuclear fission at this moment, and nuclear fusion maybe one day. Jokingly, I tell to the people that we are talking about sun today, that we use the solar energy, etc. But you know how solar energy comes from? It is also a secondary source of energy. It is happening because of the nuclear fusion at the sun. And once that fusion is over, all hydrogen is burned, probably this universe will also not exist, because then everything will be over. So whatever that may be, God has preferred nuclear energy for the sustainable development. So sun God, if you believe sun is a God, and you ask as a consultant what we should be doing for solve our energy problem in the earth, probably he will tell, take energy from me as long as you want, but be Atmanirbhar, be self-sufficient. Make your own fusion reactor in the earth. Bring the earth to the sun rather than taking something from the sun. That may be the last thing we should be doing after the fission is over. So very simple nuclear fission. You know, we use 3 elements, or presently one element, that is the uranium-235, and when you heat with a neutron, it will be splitting into 2. In this process, you will get lot of things. Neutrons will come out. You will get lot of energy, and you will see many invisible particles. One particle comes out, which is for fundamental research we are using, is antineutrino. If on an average in a nuclear process 6 neutrons comes out, 3 neutrons comes out, probably double the number antineutrino comes out, and that is another fundamental subject I will not be touching here, because that is also a mystery. If Higgs boson, which gives mass to everybody, called the God particle today, this antineutrino or neutrino is very mystery, nobody has understood fully. It is called ghost particle of the universe. So you get from this reactor only, plentifully, but we have not tapped it enough today, but probably we can tap to understand it. But I will be concentrating on the neutron and the energy, and this energy can be plugged into a fission reactor, and you can take the energy, and energy can be converted into the heat or whatever you want. Anyway, this is the periodic table I am showing, but it is a meaningless. Out of entire periodic table, 2-3 elements we will be using it. One is uranium, maybe plutonium, and maybe thorium. These are the 3 things we will be using for fission reactor. And the first in the periodic table, hydrogen. Hydrogen and its cousins. It has a 3 cousins, if you know: hydrogen, deuterium, and tritium. They belong to the same family, but their mass is different. And they are also very good candidate for fusion, whose sun is using some of them. And today here, I will be using uranium as a target for fission. Sir Govil sir, namaskar. Thank you. I was reminded you. And this is a little technical slide. You don't have to worry too much. You don't understand what I am showing. In the earth, the element which we are getting, that is called natural uranium. In nature, what we get it, and it is not the uranium which you require for the nuclear fission. If you see the circle, only 0.7% it is called uranium 235, and remaining is uranium 238. It is called an isotope. 235 is an isotope of uranium, and mostly it is uranium 238, which is ordinarily not fissionable. What is used in the fission is 235. A simple thermal neutron will split it. This is what we are using today, and to use this, the right hand side shows that it undergoes fission and produce energy. This is what we can tap to produce the electricity and other phenomena. But the 38 remains as it is for a long time. It occasionally absorbs a neutron, and the mostly fission is happening in 35 most of the time, but 38 occasionally absorbs a neutron, and in this process, once it absorbs a neutron, it becomes 39, undergoes beta decay, and going couple of beta decays, 2 beta decays, it becomes plutonium 239, and another important fissile material, and it is also materials of mass destruction. And this was discovered by working with Fermi. That the Seaborg, he discovered this plutonium. He also got Nobel Prize in 1944. And but then it is a very good fissile material to produce energy. Today we can use that also. So what we do in India, we have natural uranium. In our present generation of reactor, we use natural uranium. Natural uranium, when the neutron comes out, it will create a chain reaction, but the velocity of the neutron, the way it comes out to the fission, is very high. It cannot create another reaction in uranium, so we need to slow down its speed, and to slow down without absorption much, we use some variety of water. It is called heavy water. I don't know how many of you know heavy water. Water is H2O, but in water there is a 0.02% of heavy water, that is called D2O. It is also colorless. You may not, if you know it, that is the heavy water. What we do, we have a technique to enrich that water to heavy water. Almost more than 99% we enrich it. Then this heavy water we use in a reactor, so it slows down the reactor. It acts as a moderator. After neutron slows down, fission takes place, and uranium also on the other side slowly start converting to plutonium. So once you take out the fuel, after some time, once it is burned, you will be seeing the original fuel will be containing uranium 238, plutonium 239, and all fission fragments, which you don't see naturally. So that is what we call a spent fuel. When you take out the spent fuel after some time, it is not a waste. Many people in the Western country, they say it is a waste, they dump it, but we call it is a wealth. I will tell you in a couple of slides. We take out uranium, spent uranium 238, we take out plutonium, and we take out almost all the fission products. They are short-lived fission products, they are radioactive, and they are alpha, beta, gamma emitter, and we can use them for medical purposes. We are the only country, unique country, we have the reprocessing techniques by which these fission fragments are taken out, and instead of calling them waste, we use for the medical purposes today. That's why we are the pioneer in medical treatment, and whatever people call waste in India, we call it wealth. We get the wealth from the waste, and this is our program is. So summarizing this nuclear power program, I should say, we have a 3-stage program. This is what Bhabha started. In the first stage, we want to use natural uranium. We don't have enough source of natural uranium. Whatever we have, we want to use that. 35 is consumed for nuclear reactors, but cleverly, the 38, which is 99.9%, we slowly converted to the plutonium. So second stage, we got enough plutonium and uranium 238 is there. That you put in the first reactor, where we don't cool the neutron. In first reactor, plutonium is a good agent to create fission and produce more neutron, and it can burn uranium 238 also. So in the second step, we use plutonium and uranium 238. Also, we can use thorium. Everywhere thorium is more than uranium, and in our program, what we will be doing now, we will use plutonium and thorium. Thorium will get converted like plutonium after 2 cycles. Right hand side shows the way uranium 238 gets converted to plutonium 239. Thorium 233 absorbing a neutron can also got converted to uranium 233. That is also fissile like uranium 235. So what we are trying to do, we are in the first stage today. Second stage has started just, where we are using plutonium, and third stage we will be using uranium 233, which is not found in nature, but we can convert from thorium to uranium 33. So this is the 3-stage program of Homi Jahangir Baba. 1, 2, 3. 1 we have matured, second we have started now, and third we will be entering at any time. If that happens, we will be not only free in the nuclear power, we will be also free from nuclear fuels. Now sometimes we have to depend on natural uranium from other countries, and the fuel is a geopolitical situation. It can dictate you something sometime or other. But once we started from the thorium, we will be completely independent. Nuclear power, green power, sustainable power. That is the motto. And today we are running 24 reactors very safely, and some of the reactors continuously been running more than 900 days, more than 2 years, more than 1 year, and no plants globally anywhere will run continuously that many times. It is only the nuclear industry of Department of Atomic Energy, so many technical experts, so many know-how, so many safety. It is running continuously without any fear, and we will be increasing it. And if this happens, it is a clean energy given to everybody. Uninterrupted clean energy. You don't need to save also, store also, anything. Just put into the grid and it runs. This is something I repeat. So now we call pressurized heavy water reactor in the first stage, which use natural uranium. Second stage we will be using plutonium, fast breeder reactors. Third stage will be thorium reactors with uranium 233. That is the third stage, and we are very much following it up. And this I will skip it. Now I come to the national security. This is the slide I have borrowed from Dr. Chidambaram. See, you will see in India we celebrate many days. February 28 we celebrate Science Day, is the discovery of the Raman effect. Mathematics Day we celebrate in December 22, the birthday of Srinivasa Ramanujan, the magical and natural genius, you know it. Engineers Day we celebrate in September 20, the birthday of Visvesvaraya, the greatest engineer India has produced. And one more day has been added now in 1998, May 11, that is called Technology Day. I do not know how many of you remember what is Technology Day. Probably none. Technology Day is the, okay, let me remind you another episode. This March, Oppenheimer the movie, Christopher Nolan, got Oscar. That you know? that got Oscar, 7 Oscars, best director, best actor, many things in best category. And it is a biopic of Oppenheimer. It is called American Prometheus. Prometheus is a person, or Arista you can call it, who stole fire from the god Olympus, and then they punished him because they believed he has stolen the fire and given to the mankind. And nobody realized, because everybody thought that fire will destroy the mankind, but then it was not like that. That fire was used for the mankind. That is what called Oppenheimer is called American Prometheus. He only discovered this atomic bomb. He is called the father of the atomic bomb, which I was talking about 1945 detonated. I showed the second picture. But then it is not destroying the something, but it is the creation of the technology. Mastering that Trinity test, up to that it was all right. It is the highest demonstration of technology, how the energy can be demonstrated in the controlled way. Bomb is an uncontrolled chain reaction, but the Trinity experiment is a controlled uncontrolled experiment, I call it. Up to that it was all right, and it is not one man's job. Although Oppenheimer did it, it is a team of Manhattan Project people work. Fermi, 1942, he demonstrated chain reaction. Otto Hahn discovered the fission along with his colleagues. Then plutonium, Seaborg discovered the plutonium which was used. And then plutonium, you know, Chidambaram says it is a physicist dream, engineer's nightmare, because anything you do engineering with a plutonium metal extremely difficult, because it has a 6 phase. It is called allotropes, alpha, beta, gamma, delta, like that. And with the temperature, if you little temperature you change, the shapes will be changing, going alpha phase to beta to gamma. So it is never stable. But if you want to do an engineering, you want to make a device out of plutonium, you want a device for whatever purpose, then you will never able to do it, because the moment you start welding, temperature will be going, it will be fluctuate. There is a genius scientist, Professor Smith, he is a metallurgist. He was working in Los Alamos. He tell 8.3% of gallium, and once you put a alloy, make it alloy, it becomes absolutely stable in the alpha phase, which remains for a longer temperature, and that is the geniusness. So that's why Chidambaram says it is a beautiful element. Nuclear property is beautiful of plutonium. Fission property you can describe by, sometimes you can describe it as a liquid, sometimes you need cell model to describe. That is a beautiful object, but engineers nightmare. But when engineer and physicist work together, it became a surprise. Now we have tamed plutonium such a way, anything, everything you can do. And Chidambaram says, when nuclear weapons are tested elsewhere, everybody has a connection with everybody. Russia has it is a Venn diagram of nuclear weapons. Russia has overlap with USA. UK was part of USA. France had a little bit of that circle. So also Israel, South Africa, China, Pakistan, everything. But India stands isolated. Nobody was, we are completely isolated. India started because in 1974 we did an explosion, Pokhran explosion, that happened 50 years back. And because of that, India became a country of denial, technology denial. And nobody was sharing anything, nor we are sharing to anybody. So plutonium separated in BRC by Dr. Setna. Metallurgy developed, Professor Brahmaprakash, which we are talking about, product of this university. Fuel developed, Bhabha made the reactors, engineering developed, and finally in 1998, India also did what is called Operation Blue Star, Operation Shakti, and Atal Bihari Vajpayee named that day 11th May 1998 as a technology day. That is what I said, the technology day, and it is coming in couple of days. We will be celebrating again technology day. So think the Oppenheimer movie. If you say in the West there are Oppenheimers, it is a group of Oppenheimers. India is not less. We have several Oppenheimers starting from Bhabha, Setna, Chidambaram, Ramanna, everybody. So I call them, if USA has Oppenheimer, India has Desi Oppenheimers, and I am proud that we belong to the family of Desi Oppenheimer, a technological house. And why I am showing you this? Because of this, that people felt because of denial, your economy will go down. This is some study done by those times, data available after 2004. He said after 98, economy has grown up, nothing has happened. There is no dip around that time. It is a fear we have, and it is because of, you know why? This, I read as it is, a talk given by Chidambaram in Indian National Science of Engineering. National doubtness is that your enemy may get adventurous. So this is the principle behind nuclear deterrent. So when I say we are secured, nationally we are secured, this is what I mean. We are secured, and nobody can threaten us, and we can engage in the national development or science development otherwise. You are secured. Then I come to the health security. I have some time, I have crossed. Okay. So I come to the health security. When I say health security, I will be concentrating on cancer, and it is known the radioisotopes. Anything which is not found in nature, if you produce them, they will be unstable. Using a reactor or an accelerator, you can produce some elements which is unstable. These are called radioisotopes. They will decay by emitting radiations, either alpha, beta, gamma. That is what we call isotope. But they happen to be the greatest friend of the mankind, and we prepare nuclear medicine out of it. And it is primarily now using primarily for cancer diagnosis and therapy using alpha, beta, and gamma radiation. Let me say how nuclear energy or how the department doing towards fulfilling this nuclear medicine. Cancer burden in India, you know, it is expected that the burden of cancer in India will increase from an estimated incidence of 1.3 million cases in 2018. Our population is, to remind you, in 18 it was 1.3 billion, and cancer is 1.3 million, huge. And to about, it will go to 7.7 million. And out of this cancer patients, I will say that the burden gone to the Tata Memorial, 10% of that, where it's 1,30,000, we are treating in Tata Memorial Center, spread all over the India. You see, these are the 11 centers at this moment. First one is Mumbai, Tata Memorial Hospital, all of you know. They have a research center in Kharghar, Mumbai. Then we have Mahamanya Pandit Madan Mohan Malviya Hazar, Banaras, there are 2 Homi Baba Cancer Hospital. And in this part of the country, we have 2 Homi Baba Cancer Hospital and at Sangur and Mulanpur, and plus other places. And the idea is we use radioisotope for scanning. Either it is a PET scanning or SPECT scanning, and nuclear medicine is a must. Like a PET stands for positron emission tomography, SPECT stands for single photon emission computed tomography. Cobalt 60, which emits gamma, it is also used for therapy, agriculture, everywhere. It gives a high energy gamma rate, but cobalt 60 you don't get in nature. What you get in nature is cobalt 59. 60 is an isotope. So cobalt 59, you put a neutron into it, it will get absorbed, it will become cobalt 60, it will become radioactive. 59 is stable. The moment you make 60, it will start emitting gamma rays, a long half life, and that can be created inside the reactor only. Put a stable 59, after some time you take it out, you will have 60 components. This is how reactor is used to manufacture radioisotope, which ultimately can be used to produce nuclear medicine. One example I will give. Okay, I have taken, this is a little technical, but it is a formula of glucose. Glucose is actually, there are 6 carbon atom, 12 hydrogen atom and 6 oxygen atom. Left hand side is a glucose. It goes to our body very easily. It mixes with the blood, but glucose has a property, if there is a tumorous cell, it is more alcoholic. It drinks more glucose than the normal cell. So now what you do? There is an element called fluorine 18. Fluorine 19 you find in nature, but fluorine 18 you don't find. What you do? You take oxygen 18. Oxygen 18 is also a rare thing you find in water. Water is oxygen 16, but 2% of water, like heavy water I told you, oxygen 18 is also 2%. Enrich the water. We have technology to enrich it from the water. We can make oxygen 18. Otherwise, people are importing. Department has a technology to enrich oxygen 18 from water or from heavy water. That oxygen 18, you put a proton into it, like a cyclotron used, bombard with a proton, oxygen 18 will become fluorine 18, having a half life of 2 hours, and it emits a positron, not electron. It's a brother called positron, antiparticle of electron. And this fluorine 18 2 hours life, what you do? Chemically take out is this one of the OH ion, which I have shown there in the red square, and attach this fluorine 18 and inject to the patient. It will go to a tumorous cell, and fluorine 18 will start emitting radiation. This is what happens. So the glucose, which is containing fluorine 18, will emit one positron, that is called E plus, electron plus, and after going to the tumorous cell, electrons are plenty. It will combine with the electron and annihilate with the gamma rays, and that gamma rays will come out. 2 gamma rays will come out. You put 2 detectors outside and track where it is come from, and see that which part of the body it came from. That is, wherever it goes, that is the tumor person. It is the positron emission tomography imaging. This is what every hospital does today, but nobody, very few will be knowing where fluorine 18 is coming. Even though fluorine 18 is coming from an accelerator, nobody knows where oxygen 18 is coming. It is coming, maybe coming from you can import it, but if you want in India, it is coming from Department of Atomic. This is how our contribution to the nuclear medicine imaging. Cobalt, it can be, there is also another, and similarly I told, I am showing a couple of reactors, because inside the reactor, these are the research reactors. Earlier I showed power reactors, they produce power. These research reactors are very, very small. Only we take out neutrons. and neutrons used for other research purposes. And these neutrons, when I told you when you heat cobalt 59 and cobalt 60, there is an element called lutetium. Lutetium 98 you find naturally, and 99 you don't find it. Again put into the reactor, 98 it will become 99, and that is attached to a molecule. It is a very good medicine for a prostate cancer treatment, and we produce and give to the breed Tata Memorial. There is another element called molybdenum 99. Molybdenum 99 you don't get you don't get in nature again. 98 is obtained, but you put a neutron it will become 99, and one beta decay it will go technetium. It is again a gamma emitter, and technetium is used 80% in the hospital for SPECT scanning. One is PET scanning, another is SPECT scanning, and rest of the medicines if you want, like iodine 131, 35, they also made beta and gamma. Thyroid treatments. So some of the radioisotopes can also be used by treatments, because once you identify there is a tumor, again use same radiation to kill them. So it is a both complementary to each other. So today, if you see, almost all the radioisotopes, 75 of them or more than that, we are producing in the Department of Atomic Energy, partly in Dhruva reactor, which is in BRC, and it is marketed by BRIT. This is the Apsara reactor. It is also Bhava did the first reactor in 1956. What you are seeing, I am not showing you the reactor building, I am saying what you will see inside the reactor. A blue light. You know what is this light could be? In the reactors, there are neutron comes out, and this excited fission fragments, they are decay emitting electrons also, beta decay. There are electrons. These electrons, some of them moves faster than light in the medium, a process which Cherenkov discovered, and it is a visible blue light. This is their light, Cherenkov radiation. And I take little detour, allow me to tell that this light you will not see in natural, it is an unnatural phenomenon, you will not see in nature so easily. You will see in the reactor only, or you may see the sky when charge particle moving, gamma rays finally converted. You may see the Cherenkov radiation. There are certain telescopes people put in the sky like Cherenkov detectors, they are there to detect it. And there is a story in Odisha, I don't know how many you know, there is a Lord Jagannath in Puri. And before it was in this form, Lord Jagannath was getting worshipped at another place close to Puri, Lord Nilamadhav. And when it was not a structure, it is not in any form, it is a bright light looking blue color like this, it is a Nilamadhav. But then what happened, after making the temple in Puri, King Indradyumna, he wanted to searching the god, and the god appeared in the dream and say, I am appearing so and so place in the form of Nilamadhav, you go and bring me. So he sent his minister Vidyavasu, and it was being worshipped by Sabur king Vidyavasu, and was worshipping, and he was not showing to anybody. But this Indradyumna's agent hidingly went there, and by the time he reached it, God disappears, because you cannot steal the God. And then there is a story, and he reappeared, and that Puri temple is built all. But I tell to the people, my friends in Odisha, when I leave Odisha, I say I am leaving the land of Jagannath, Lord Jagannath. But then immediately coming to BRC, I discovered that it is the place of Nilamadhav itself. So Odisha has Jagannath, Department of Atomic Energy has Nilamadhav. That's what I say to people. And this Nilamadhav in form we are using somewhere or other for service of the nation. Okay, let me summarize this part of the things. What I want to see, all the radiopharmaceuticals along with this radioisotope, along with radiopharmaceuticals, we have now the formulation in the Department of Atomic Energy, and we supply to everybody. Just you see, first one is called yttrium-9 dotatate. It is an injection. It is used for neuroendocrine cancer therapy, and you can also import it. If you see the price, it is 2 lakhs per injection, but our breed is selling it 80,000. Similarly, you take anything like gallium PSM-11 for prostate cancer injection, prostate cancer. If you buy it is 21,000, but you will get less than 10,000 if it is marketed from the Indian. So everything we are controlling the price, And although we don't have sufficient, still our demand is much more than what we are supplying. People are importing, but because of this, even it is a 25% of the requirements today, which we are producing, probably indirectly we are controlling the international market. If you were not there, probably the price would have been much more. So the Brit is controlling the price, and what we want to do now, we want to make a dedicated isotope producing reactor, research reactor. Instead of taking the neutron here and there, we want to produce all radioisotope, which is very advanced stage. It will be made in a PPP mode, public-private partnership. We will make the reactor only to produce isotope, and the private fellow will be marketing it. And we are thinking once it comes in a couple of years, by end of this 2030, it will be the largest producer of the radioisotope in the country. And out of which we will be using only 25%, remaining 75% or so will be able to supply to the globally, to other countries for the people. And this is what going to happen. So this is what I told, that total production is very less, and we will be producing isotope producing reactor, and then we can claim there were Atmanirbhar in nuclear medicine. A day is coming to be very soon. This is on the healthcare. This is my last slide. Very interesting slide. You can see the right hand side. It is a silver plate, top one. It is a silver notch, but inside it has some coating of ruthenium 106. Ruthenium 106 is an element you don't find anywhere. Once you take out the spent fuel from the reactor, when you take out the spent fuel, it contains many things which was not there before. Because of the nuclear reaction, you see the fission fragments, and one of the fission fragment is ruthenium 106, which is a beta emitter. And we have a technology to take it out. We have a technology to take out cesium, which is a gamma emitter. We have a technology to take out ruthenium, which is a beta emitter, short-lived beta emitter. We have a technology to take out americium, which is alpha emitter, which can be used in radioisotope heating unit. In NASA, our ISRO has used a couple of them, sent to the Chandrayaan-3. These are the isotopes have given to them. But what I am showing here, in the inner side, we have a little coating of this ruthenium 106, and it is acting as a eye plug. Those are having eye cancer, ruthenium 106, you take it and put this notch. So beta will go and kill the tumor cell, and after a couple of treatments, eye will be cured. It is a real practical one. You can see the left hand side, middle one, operation is going on, and right hand side, as you see, out of 4, the last one has been cured, first one is a tumor. And this is only possible by using this ruthenium 106. It is a beta emitter extracted from the nuclear waste. Only we can do it. Not many countries having a nuclear reactor, and only Germany is exporting it. If you buy from German, the price will be probably close to 10 lakhs, and from we are marketing it around 50,000 because we are manufacturing. This is what the technology is and the power of it. This is all over. Then I get to the another 20 minutes I will take. This is going to what we do about the food security. When I say food security, idea is very simple. You know that because of the climate, many things are, even look the nuclear agriculture, simple agriculture, you find that yield is not good or yield is diminishing. People are using hybridization. Hybridization means you are doing the genetically you are modifying them, which is not good because the original variety you are not able to preserve it. And so what we do mutation breeding. Mutation breeding is a natural growth. Still, if there is a little bit tampering in your gene, DNA sequence, naturally, you will find slowly property will change. But it is not genetically modified. It is a what we call mutation modification, and that is very natural. With this natural, if you do this, your property of the parents will be preserved, and maybe something new will happen. For example, I have a plant, rice plant, very tall, and it is you will say during the harvest season, if there is a wind, it will fall down. Lodging, they call it. But I can do what I do, I can do a nuclear mutation, take seeds, put little bit of radiation, gamma radiation, and some of the DNA will get bond will break inside in the cell, but then cell will start repairing it. You put the appropriate dose so that it is able to repair. But in this process, little bit mutation will also happen. So you throw those seeds in the field and see, look like Mendeleev, look at the plants. Some plant will be short, some plants will be having high yield, some plant will be having water resistance. So like this, after 2-3 cycles, you see who is the best for you and pick it up. That is called nuclear mutation. And natural mutation, if you wait, it will take a long time. But if you put a little bit of radiation, it will be faster. You can induce mutation and pick up what you want. This is what we are calling nuclear agriculture. Today, BRC Trombe variety, we have developed 61 such varieties of seeds in these categories. This is an example. This is the latest category of a rice variety in Chhattisgarh. They are called Dhruvraj. Dhruvraj is a very popular rice local variety, but slowly people are not using it because yield was very less, height was very tall, maturity date was large, so it was not good for the farmer. So our research, we have brought out the now varieties. It is called Trombe Chhattisgarh Dhruvraj mutant, which has property like lodging resistance. Right hand side you can see semi dwarf, 90 centimeter tall. Maturity duration has come by 20% less, 135 days, and yield has gone by 20 to 30%, 5 tons per hectare. One example I give you. It can be, in principle, it can be done to anything. The principle is that only, that is what's called nuclear mutation. Recently, it is a Trombe Konkan Khara area. Rice never grows in the salty area, but two varieties has been within Trombe Konkan Khara, approved for release by state varietal release of Maharashtra committee. And it has a property like salt tolerant rice genotype. It can grow in the coastal saline soil with tolerance up to high salinity. Semi dwarf, 125 to 130 days maturity, middle late duration. Average grain yield 4 tons per hectare, which is nearly 15 to 20% more. And this has been released. It is not models. It is too color. Okay. Oh, पीछे वाला ये? पीछे वाला? चलो आगे चलो. Okay, we will see how as long as it moves. So if you see now, these are the 6, it is all categories: groundnuts, mustards, soybean, sunflower, linseed, rice, urud bean, mung bean, pigeon pea, cowpea, jute, sorghum. This is something I am showing. It is a nuclear radiation technology for the farmers. And today, if you are taking Italy in Bombay, 99% probability that urud dal would have come from the Trombe variety. This is the penetration in the Maharashtra. But then unfortunately, you cannot take this to the all over India because, as I said, it depends on the local conditions. So if you want to develop your local variety, similar exercise has to be done in the local region. And this is one mammoth task, but this is one job we have been taking in the Department of Agriculture. And we have penetrated most of the country. You can see wherever there is arrows, there are this agriculture, nuclear agriculture, our seeds are there, but not enough. We are too big a country, and this is only 61 varieties. But in principle, it can go to anywhere. And it is more meaningful because now we are seeing, we are telling global warming, probably this radiation mutation probably bring out some seeds, some agriculture which will tolerate the global warming or this temperature. And there are much more. I don't want to take much time. See, we have a hydrogel. It is a bioorganic gel, and polymerized after putting the radiation. Capacity has gone up. It will like a powder. If you put in water, it will suck 500 times the volume water. So what you do? Suppose there is a arid land or a land where it doesn't rain. In the soil, you mix 2-3 spoons of this powder and mix it. and once it runs or you give some water, this gel will swell 500 times and retain the water, and afterwards it will slowly release. So that the area which you don't have a good monsoon, put this gel, and you don't have to give the water every day. This is a powder form, BRC hydrogel. And one example I am giving, right hand side, it is a control of what we call bhindi or ka, and left hand side they have put some hydrogel powder, and after 1 month this is the condition, and this is the condition after harvesting. Left one is control, right one is the hydrogel treated water, not same water, same condition, this is the yield. I go on further. This you may be knowing that potatoes and onions, food preservation, and today in India, although we are producing a lot of agriculture produce, but most of them 40% getting wasted due to lack of storage and also water loss. But and onion is one example I am taking because it is one commodity in Maharashtra. It is producer-led plot, and onion in Maharashtra control the politics. You can win an election if you have controlled the onion price. It can go to 100 rupees in time. So that's why we did an experiment. What we did in the laboratory, we have been doing, take the onion during the harvest before it loses its water content, put some amount of calculated radiation, gamma radiation, harmful pathogens will get killed, and after that under certain condition of humidity, put in the cold storage nearby and store it. And we have seen if you don't do radiation and put in the cold storage, you can survive, keep it for 3 months, and there will be water loss also, weight loss. But this technique we have seen for 8 months, you can keep it, preserve it without losing anything. You cannot make out, for example. Anyway, it is not moving properly, so I will just keep on telling. This is the onion you see, we have done an experiment of 1000 tons, treated with the radiation, kept in the cold storage, and after 8 months, look at the shape, you cannot make when it was harvested. It is as fresh as harvested. And this is one technology, food preservation can be used. Today, Ministry of Agriculture, NAFED, they are trying to adopt this in a mass scale. So every state they should have this food storage technology. You can apply to, in principle, you can apply to any vegetable, perishable vegetable, starting from tomatoes, onions, etc. This is the nuclear food preservation. So I talked about nuclear agriculture, nuclear food preservation. Similarly, this nuclear radiation you can apply anywhere in industry. You can you think anywhere. So this is where the technology is required. Since the computer is not cooperating with me, potatoes. Let me now see that couple of slides in basic research. Maybe not so important basic research, but you can use neutron to study. It was realized as earlier 1994 by two scientists, Brockhaus and Schul. The neutron diffraction helps to determine the structure of atoms, whereas inelastic scattering allows to investigate the dynamic behavior of materials. And both the scientists were awarded Nobel Prize for this discovery. And therefore, where you get these neutrons, reactors are a very strong source of neutrons and are used for basic research. This neutron in the form of scattering has been a very important tool to study matter and materials, ranging from fundamental condensed matter physics to nanomaterials to materials for energy conversion and storage. The ability to probe structure and dynamics over a broad range of length and time scale is indispensable in areas that include hard and soft magnets, quantum correlated materials, high tissue superconductivity, multiferroic ferroelectric and thermoelectric materials, etc. There are to get this neutrons, we have two reactors in BRC. One is Dhruva, another is Apsara upgraded, which is working. And both these facilities are national facilities available for neutron beam research all over the country. All university, all of you can use it. This is the facility around the Dhruva to do all sorts of experiments. And you have all modern facilities, single crystal diffractometer, neutron deflectometer instrumenter, small angle neutron scattering, powder diffractor, high Q, whatever you name, all are equipped with around this reactor facilities. And also, if I don't tell more, but I can tell couple of things. Department In addition, what the universities, Punjab University and many others, we are part of the international collaborations, what you call mega science project, because it cannot be done one person. CMS experiment, ALICE experiment, what you may be knowing, it has its genesis in the department itself. They are done at CERN, they are done in Fermilab. But what I am showing here today, we move in the line of Atmanirbhar Bharat. Even mega science is also Atmanirbhar now. We do in the country and we make other people to come and use it. One such example is GMRT. We are all very proud of it. Professor Gobind Swarup started. It is part of the TIAPAR. It is called National Center of NCRA, Radio Astronomy. It is called Giant Meter Wave Radio Telescope, very close to a place called Pune, working. Everything is made in India, the telescope. It has 30 antennas spread over 50 kilometers. And it is an international hub, people do come and use it. It produces world famous papers and research output. We have another telescope that is called Major Atmospheric Cherenkov experiment. It is in Hanle, Ladakh. It is installed couple of years back. It is one of the largest telescope in the Asia and second largest globally, 21 meter diameter, and it is also being used to study gamma rays coming from the atmospheric origin. We have a LIGO, Laser Interferometer Gravitational Wave Observatory, and Hingoli district of Maharashtra coming up. It is a third one in the international collaboration. Two are in United States. The third one is in India. It is also international collaboration. And we have another collaboration for fusion research, International Thermonuclear Experiment Reactor at France. And all those things collaboration. And the first four are for basic and fundamental research. The last one is a research which is going to be the game changer by end of this century, tapping energy from nuclear fusion. And that is the day we are waiting for, and India pursuing it very vigorously for this research. Thank you very much.
Thank you so much, sir, for this informative talk. We can now have a few questions and comments.
Good afternoon, sir. It's an honor to hear from you and to meet you, sir. I am Manish Gupta. I'm junior to Vikram Han, sir, from Punjab Engineering College. My basic question is, we have few of the atomic centers. Why are not we able to harness electricity, or when are we able to harness electricity for use in Indian sector, sir?
Yeah.
Indian sector or the domestic sector, electricity harnessed from nuclear reactors, sir.
No, that is not true. Like we have our share of the nuclear in the total energy mix of renewable is only less than 3%. It is not that we are not able to harness, we are not able to proceed further, because nuclear is something I need a land to make it, and we don't get enough land to make it. And if you have to progress faster, there are problems. Where to put it? People have to accept us that it is one of the must-do source of energy for the future. Whether it is the 24 reactors which were running, it was running 24/7. It is unstopped. So whenever it is connected to the grid, it is continuously giving. But then it is not enough. We have to put more. So issue is not that why we cannot give it, why we cannot give the energy from electricity, but the issue is we are not able to build more. Not because of our incapability, but because we are not getting conducive environment to make it every day.
एक्सक्यूज मी सर, मैं हिंदी में पूछ सकता हूँ क्या?
हाँ जरूर.
एक एटॉमिक प्लांट पंजाब के मानसा में लगना था, वो विरोध थे, हरियाणा हुआ क्योंकि
स्पेसिफिकली फॉर गोरखपुर हरियाणा हमारा 4 प्लांट आने वाला है, 1, 2, 3, 4. अभी इनका सॉइल कंडीशन थोड़ा खराब है, क्योंकि न्यूक्लियर प्लांट जब बनेगा सॉइल भी बहुत अच्छा होना पड़ेगा. हम जैसे सोचे थे ऐसे सॉइल नहीं मिला हमको अलूवियल सॉइल मिला, इसलिए हम टेक्नोलॉजी से देख के इसको कैसे बनाएंगे इसके हिसाब से हम आगे बढ़ रहे हैं, इसलिए थोड़ा डिले आ रहा है। बट हमारा भी मानना है कि मैं गोरखपुर हरियाणा का बात नहीं करूंगा, पर जितना अभी है हम 2032 तक सोचते हैं कि हमारा और 14 इसी टाइप का रिएक्टर आ जाएगा। ये होने के बाद हमारा कैपेसिटी 22 गीगावाट हो जाएगा। अभी जो 7.5 गीगावाट है, अभी 2032 तक हम ये सब गोरखपुर हरियाणा मिला के हम 3 गुना ज़्यादा चले जाएंगे, ये हमारा मानना है।
May I, sir?
Yes.
So from an industry perspective, I have a question. Renewable energy today,
Closer.
renewable energy today, if I have to put up a 50 megawatt solar power plant, I need 150 acres of land, which is very difficult to get, expensive, and all those things. I observed that Hitachi and GE today have collaborated, and there's a 50 megawatt energy box that they have been able to commercialize.
Can you, sir, repeat? I'm not able to hear you. Mic if you hold, or give a better mic. Or if you don't mind, if you come a little closer.
Let's look at the renewable energy perspective in the country, where, for example, for a 50 megawatt solar power plant, I need something like 150 acres of land, and the cost of the land and all that comes into play when the project cost is evaluated. I also understand that GE and Hitachi today have been able to produce a 50 megawatt energy box, which can be put up commercially for supplying power to industry, the grid for any purpose, and so on and so forth. And this power box, I also understand, is commercially movable. You can change the location as well. Now, don't you think that would be a game changer for a country like India? We've spoken a lot, we've understood a lot from your Atmanirbhar perspective, and I think in terms of expertise, there's nothing that we are short of here. First of all, number two, if this kind of a product can be brought into the market, it can be brought into the country, I save so much on land, I save so much on the project timelines for bringing up a solar power plant, and it's renewable in any case. So that was an important observation which I thought I'll share with you.
I agree with you. The G, what is the source of energy in G? What you told, the source of... No, I have to see there could be a catch. See, 50 megawatt, it is a category of a micro modular reactor which people are talking about. We are also working about, but you see that one is to see that once you have a nuclear 50 megawatt, probably G might not have thought what you will be doing with the fuel. After some time you have to take out the fuels. The box looks good, but after some time you have to take out the radioactive materials. Then G has to think how will manage that, and continuously who will give you the fuel also. Because tomorrow you don't get uranium, then your box will be dead. And that security of the fuel, security of managing the waste, which is radioactivity, it has to be thought in totality. And we are also working, maybe now it looks like a box, but that box will become a problematic later on. When you start changing the fuel may go for long, but one day you have to address it. These are the problem, but people are, that's why now people moving towards small and modular reactors. 50, people are talking 5 megawatt, and not only electricity, they are using to produce green hydrogen from the heat. So all will be moving, but that moment will take time. But a country like India, the amount we need is 50 cannot fulfill your requirements. You need a bigger one plus the smaller one. So that is the approach we are doing it, because if you have to go more industrialization, this a pocket of 50 megawatt is not sufficient when you are talking of 500 gigawatt by 2030, and it will be much more when you go to the 2047. So energy, it is I agree, it is a window of limited opportunity to some people. But if you see globally as a national viewpoint, you still need much more. I agree, it should be there.
Good afternoon, sir. Myself, Dr. B.S. Sandhu, currently President of Indian Society for Radiation Physics, and your subordinate, Dr. D.K. Sawal, Balvinder Sapra, then Dr. Tej Singh. They are also associated with us, and Dr. V. Venkataraman from IJCAR, he is also associated with us. Presently, my emphasis is that we must have the nuclear program for detections of biological weapon, chemical weapon, and the drugs which are being smuggled to India by way of various modes. And in US, we were simply able to detect the presence of anthrax in any capsule or in any form. We were able to that one. But in India, we are not emphasizing on the use of these nuclear radiations or nuclear technology for the detection of biological, chemical, and these drugs. Any suggestion from you?
No, not a suggestion. I am on action only in this point. For example, what he is asking that smuggling of chemical, biological, and radiological materials to the India. That's what you are telling, and nuclear technology to detect it. It is very much there. And today in the border, if you see artery border, people are deploying them based on the nuclear technology. They are calling dual energy cargo scanner, and they are imported one. But we have also now made, for example, if you use a dual energy X-ray, with this technology existing with BRC now demonstrated, so it can detect, it is X-ray penetrate, but it has a limitation, but it can detect, suppose you are not hiding a container, it can detect a gun also. But if you are smuggling with a lead seal, it cannot detect it. But what we are doing now, we are using muon tomography. And you know, muon is, nature gives a lot of muon. And we have a high energy physics community as a detectors. And using these detectors, muon can be detected, and this technology can be added to the cargo scanner. And this is very much going on outside. India also are developing, but we are behind. But what you suggest, this technology very much can be used. Muon can be used penetrating device. If you are hiding a gun inside a box, it can penetrate. And once you suspect, do more probing and use X-ray. And also neutron can be used as a neutron source into this, which can do also radioactive materials. So all are there, people are working, but should be done. That's what I am telling.
More emphasis must be there because
that's what I told.
Applications.
That's what I told, that I don't have a suggestion. We are in action into it. It one day it will come out.
Good afternoon. Simple question on food security. It's two-part question. One is, are there negative effects of the radiation that goes into the food? If there are, is there a communication needed for the common public that there are no negative effects of food radiation when we use nuclear energy?
See, this is what we have been trying to explain, that whether radiation has any effect on food material, and after you take, whether it will be harmful. Before answering your question, let me give an example. Today, any spice or mangoes, those are in USA, Patel store of USA, you will be seeing mango gone from India, Kesari mango. You cannot export mango to US without irradiating. So that is the acceptance level in United States of America. Because in the mango, in the seed, there may be sometime insects. Unless you put the radiation, that insect will not get killed, and USA department, their FDO will not accept it. Their inspector comes, they see in the irradiation plant, and in their presence you irradiate, and then only mango is exported. Same thing for spice. So the answer is that there are certain countries, European countries and American, without seeing a tag of irradiation, they will not take the food grain from India or any other country. So it has been accepted. जो India का बात है, थोड़ा acceptance कम है, but I will tell that it is a irradiation, it passes through. It is like a chemical which remains, chemical treatment which remains in the food. Irradiation is just like your X-ray coming, going. You go to the hospital, you take X-ray, you get a photograph. X-ray number remains in your body. It has passes, and wherever it could not pass or a little bit reduced, that is the photograph you get. So radiation is simply similar. It just passes through, killing something, doing good for killing the bad pathogens. And that is what we are telling people, and people are accepting. Time lagega, because when the plenty of suppose onion in the belt you are producing, onion is so much, who will be radiating and preserving? They will eat the onion itself. But things are changing. When there is a scarcity, price is going up. In fact, government of India is adopting radiation technology for food preservation, going in a big way, and there is no harm. In our lifetime, you take many X-rays scanning, and nothing has happened to us. It is the limit is much less than what you are getting from natural radiation. I don't know whether I have answered your question. The issue is what I tell everybody, science and society there is a barrier. Science is getting knowledge faster than society getting wisdom. So we have to bridge the gap.
Thank you. And this is for the information of research scholars and BSc and MSc students. We have an open interactive program with Dr. Mohanty. It has been scheduled at 3:30 today. Right. So with this, let us thank Dr. Mohanty again. And I request Professor Tripathi, Chairperson, Department of Physics, to please come and present a memento. Now I invite Professor P.K. Ahluwalia, President, Indian Association of Physics Association, please come on the stage. So very generously, the honorarium, so please. I invite Professor Manjeet Kaur to please come on the stage, and I request Dr. Mohanty and Professor Ahluwalia to present IAPT Achievement Certificate and Medal to her. Professor Manjeet Kaur was recently conferred the Doctor of Science in Physics by Punjab University.
Very good afternoon. Actually, in the memory of Professor Hans, IAPT, because of very generous contribution from Mrs. Tripta Hans, instituted a silver medal, and this silver medal is being given in experimental physics, and we are at IAPT very pleased to honor with this medal to Ma'am Manjeet Kaur, and I think
I request Professor Ahluwalia to please say a few words.
I would also like to give to Professor Mohanty the special cover which was released to honor two founders of the IAPT, founder presidents of the IAPT, Professor Hans and Professor B.L. Saraf. They were both presidents of the IAPT. I would also like to request if Vikram is here to come on the stage. Okay, all right. May I also request the chairperson of physics department to come and receive one cover for the Honorable Vice Chancellor. Yeah. I would also like to request Professor Grover to please come on the stage and receive this special cover. So I hope we had a wonderful lecture, and I'm very happy that we have very many people here with us who were very close collaborators of Professor Hans, and I request that you please applaud for Professor I. M. Gobil also, who is present today in this audience. You know, when we were thinking of this program of IAPT, we talked to the physics department, and let me tell you that Indian Association of Physics Teachers has a very strong bond with physics department, Punjab University. We are 40 years old, but from day one itself, IAPT has been having its presence in the country because of the groundwork which was being done in the physics department. And I think that's a wonderful, support which has been given to IAPT. We also have very energetic, faculty here in the audience, starting from our chairperson, Professor H.K. Tripathi, Professor Vibhash Behera, Professor D.K. Mehta, and Professor K.P. Singh. I'm not able to see him here, but yeah, he's here. And many other people who have been collaborators of Professor Hans. So honoring Professor Hans also actually means honoring the collaborators of Professor Hans also. And this is something which has been instituted very nicely so that we can carry on with this kind of memory in the physics department by Vikram Hans and the family members and Mrs. Tripta Hans also. I, from the core of my heart, thank you, sir, for being so generous to us. There are a few things which I can recall about Professor Hans. I have been visiting physics department here from Shimla quite often. I have been in physics department, Himachal Pradesh University. And we very often used to meet him. And to tell you very frankly, dear students, that whenever anywhere, outside Chandigarh, people talk about an educational tour in physics, the first, place which is mentioned is, let us visit cyclotron. It is that kind of a what you call dharmasthali of physics. Professor Mohanty also mentioned about it a lot of times. I am also very happy to tell you that Professor Hans had very many contributions, not only in nuclear physics, for which he is so well known, but one of the very important foundational thing on which he worked in the northern India was under College Science Improvement Program, under which lots of books were actually generated, lot of resource material was generated. Try to imagine, something happening almost 50 years back, and those resources were made available to the students and the teachers in this area itself. I have one request to make, and I will request Professor H.K. Tripathi that please take this request to the Honorable Vice Chancellor. I wish if she had been here, that these books are still available as a publication of the Punjab University Publication Bureau. Can we really do something like this, that we create PDFs of these books, and IAPT will be very happy to post these books as a resource material on our website itself. This is my personal request also, and if that can be done, I think those books are wonderful books. They have not lost their utility. Please don't see that they were made in say 84. I think they are being sold even now in the market. So if that can be done, I think that will be a great help to us. I also want to tell the honorable speaker, when I was with him in the morning, we were talking about it, and number of times he was talking about IAPT. He had visited this department earlier also on a very special occasion of the Indian Association of Physics Teachers. That point which we made sure happens through IAPT was the following. The moment we came to know that we are going to have the birth centenary of Professor H.S. Hans, we designed a program across the regional councils of Indian Association of Physics Teachers. And we reached out to, sir, more than 10,000 students under that program, in which we used to make a presentation on, as sir in the last slide has shown, cyclotron is a harbinger of big science in the world. So what is that? What does it mean? And what was the contribution of Professor Hans and the kind of hard work which was done to raise that cyclotron, which was brought from USA here, and Professor Govil is sitting here. For 10 years, there were no publications coming, but the passion was to build that cyclotron, to make that machine live. And fortunately, it is live till date. That is the kind of spirit with which Professor Hans and the collaborators actually have worked. Also, we showed, and in fact, in a National Student Symposium of IAPT, sir, here in Punjab University last year, we showed a movie which has been shot by Janvi Falke, who was given last year's Infosys Prize. And that prize was given to her on the basis of atomic science research and its development in the country. And I think the key role in that prize has been played by that film itself on the cyclotron. And we used to show that film, and we never let students go out like that. We also used to have a quiz so that they may know that what they have absorbed or they have not absorbed. So this is something which we have been doing. So we are also grateful that BRNS is actually helping us in IAPT for the publication of the only education journal of physics in the country, that is Physics Education. If it has been sustained, it is because of this help which you give us on annual basis, and we are grateful to that. I think this lecture was a mind-boggling lecture for the students sitting here, for the audience sitting here, and it was a wonderful, discourse which was presented by Professor Mohanty to bring a connection of science and society. This was very important. Sometimes we try to see science in isolation, but that is not the case. And I think 60% of his lecture was devoted to how the nuclear program of the country is helping to reach out to the society itself. This is remarkable. There were many things which we were not knowing. I think now we have come to know about that also. When our students used to visit cyclotron, one of the things which they used to ask was this only, ये क्या काम आता है आपका cyclotron? And very often, the answer to this question used to be, ये PGI है ना, उनको हम radio isotope supply करते हैं. So that is the kind of relationship this initiative has been happening. When I was watching that film Cyclotron, I came across one important time on the timeline of that film, and that was that there was a program of bringing a accelerator facility in the Chandigarh also, for which Professor Hans worked very hard, and unfortunately he had met Mrs. Indira Gandhi also for that, but after 2 days she was assassinated. That is a very interesting moment in that film itself. Had that not happened, I think that cyclotron or the machine which is in Delhi, that would have been in Chandigarh itself. Hopefully, I come to know from my colleagues here that they are still trying about it, and I wish them good luck. To the young students sitting here, I would like to tell you, keep a tab on IEPT. Only yesterday, sir, there was one lecture online which was given by Professor H.C. Pradhan, former director of Homi Bhabha Center for Science Education. That was on the thorium initiative of producing energy. It was only yesterday we had that lecture. Very, very interesting lecture. So you can reach out to very many people via IAPT. Last month we had Professor Carl Wieman, who is a Nobel laureate, with us for about 1.5 hours when he spoke about, apart from his basic research, a program which is very dear to his heart, that is on physics education research. Bringing Nobel laureate direct on your mobile is our target, and that is what we are trying to do. Ma'am Manjeet, who is sitting here, she is the chief editor of IAPT Bulletin, and IAPT Bulletin has been published for IAPT from Punjab University, Chandigarh, without break for the last 40 years. This is not a small achievement. You can join us. We invite students to become members. Any other person who is not a member of IAPT and is sitting in this audience, please become our member, and you will see that how vibrant Indian Association of Physics Teachers is. Every year we conduct national standard examination targeting +2 students for international physics Olympiads, and the number of students which sit for the exam this year was 1,38,000 students. Try to imagine our reach. Apart from that, what we are now trying to do is that we are conducting lots of competitions for physics students who are sitting here. And one very interesting competition which we held last year was international, this was converted into national actually, National Young Physicists Tournament. It went on for full year, and you will not believe the kind of work which students did on open-ended problems. Just to give you a sampling of the kinds of problems which were asked in that was, can you use physics to find how many matchsticks are there in a matchbox just by shaking? I mean, try to imagine this question and see what is the meaning of an open-ended question itself. So, sir, we are grateful to you for accepting this invitation. Every time, sir, I was telling them, when are you going to have the lecture? They were always saying, please have patience. We are having a person who is the best in the country. And we are delighted to have you here, sir. Once again, on behalf of IAPT, I thank you.
Professor K.N. Pathak, former Vice Chancellor of Punjab University, he could not come to this function, but he has expressed his thoughts and shared a written note. Professor Behra will please read it now.
I want to request Vikramji to come on the stage and have this special cover which we released on behalf of IAPT.
Okay, friends, this is a message from Professor K.N. Pathak. He is a Professor Emeritus of this department and the former Vice Chancellor of the Punjab University. He could not come because he is busy somewhere, and he informed 3 days back. So Professor Hans actually recruited him in his expansion program of this department. He is a condensed matter physicist. So he had sent a message. I would have been extremely happy to say few words about late Professor Hans. Due to prior commitment, I am unable to attend the program in person. I am his admirer. He was not only a very good physicist, but also a great human being. I believe it is he who has made the physics department what it is today. He was an original thinker and dedicated to physics and its development. On a personal note, Professor Hans invited me to send my biodata if I am interested in a position of a reader at Department of Physics. And I got appointed, and he appointed me in absentia in 1970, and I joined in September the same year. It was very good that Physics Department and his son Mr. Bikram Hans has taken his initiative and doing his program for the last many years. Professor K.N. Pathak. And many of the students, some of may not be knowing, Professor Pathak was the former Vice Chancellor of this university, and you might have seen him several times in the first floor in his room. Okay, so this is a message from Professor Pathak.
Now I request Professor Arun Grover, former Vice Chancellor of Punjab University, to please come and say a few words.
So thank you. I'll be very brief because you're already very late. So thank you, Ajit, for coming and delivering today's lecture. So let me share with all of you, this is the second time that the chairman of Atomic Energy has come and delivered a named lecture in Punjab University. The first one was Homi Bhabha himself, the year 1964, and he delivered the Baba Kartar Singh, first Baba Kartar Singh Memorial Lecture in the chemistry department. After that, several chairmen have visited the university and delivered various other lectures. For instance, Dr. Banerjee was here to deliver the Punjab University Foundation Day lecture. Dr. Chidambaram has visited the Punjab University many times. So have Dr. P.K. Iyengar and many others. Now this lecture, so you know the chemistry department had these named lectures, Baba Kartar Singh Memorial Lecture, R.C. Paul Memorial Lecture. The physics department didn't have it. So I'm lucky that both these B.M. Anand Memorial Lecture and the H.S. Hans Memorial Lecture got instituted during my tenure as a VC. Actually, my mindset whenever I come to the department is of a student. I met Professor B.M. Anand in 1967, few months before he retired, and I had visited to enroll in the physics department, and he told me, no, you have to do a class 12 to come to gain admission into the physics department. So for a year I went to a college, and then on 1st June 1968 is the first time that I met Professor Hans as an NSTS scholar in physics. I spent a month in the physics department. And Ashwini is here, my classmate from the physics days, and all of us, we walk into the department as if we are still students of the department. So this event, like, the two named lectures are for the students. And I would like to appeal to the students and the alumni of this department to take ownership of these two lectures. Okay, tell us which national icon you want to listen, and so long as I am living in Chandigarh city and I have energy, okay, I shall respond to what you want in the form of these two lectures. Now, what is common between Professor Hans and Homi Bhabha? Professor Hans was a student of Pyara Singh Gill, P.S. Gill, at Aligarh Muslim University, and P.S. Gill was a contemporary of Homi Bhabha, and for a while, one was a theorist, the other was an experimentalist. For a while, they both worked in cosmic rays, one at Bangalore and the other at Lahore immediately after the war. One was caught in Bangalore because he came on a vacation. The other had just come home after finishing his PhD in US, and he got caught in Lahore. So one was flying after the little bit just before the end of the war, British planes, he was sending payloads for doing cosmic ray research. The other one in Bangalore was using the US Air Force plane, which had come to HAL for some maintenance. And he was flying his payloads from Bangalore. The other one was flying his payload from Lahore. And after the Indian independence, the first professor of experimental physics that Homi Bhabha had inducted in Tata Institute of Fundamental Research was none other than P.S. Gill. Of course, long story, P.S. Gill didn't stay for very long, came and set up this rejuvenated physics department in Aligarh Muslim University because all the physicists from AMU had migrated to Pakistan, so the department had to be rebuilt, etc., etc. So, a tradition of doing physics in a university department came up at Aligarh Muslim University. Of course, there was physics going on in Calcutta and BHU and Allahabad, but closer to Delhi it was. Of course, Delhi also had physics because Kothari's student Kothari was there. But doing experimental physics, doing experimental nuclear physics in a university department, in a big way started at Aligarh Muslim University and Professor Hunt. Cosmic ray started with B.M. Anand because B.M. Anand and Homi Bhabha's lieutenant or the person who succeeded Homi Bhabha as a director of TIFR, M.G.K. Menon and B.M. Anand. You can see in this plaque, they both did PhD together under the Nobel laureate C.F. Powell. Okay. So there are a lot of very nice connections and commonalities you can explore if you explore the history of this department, history of the other departments in the university. So via attending these named lectures in the university, actually you can come to know how the evolution of education, science education, research, mathematics, social sciences, economics, everything. So there, Punjab University has so many named lectures. So I would appeal to the students, they should not only attend named lectures of their department, but you have an opportunity of knowing so much about the history by going and attending named lectures whenever and wherever you can find time. So thank you very much.
Thank you, sir. We have among us Professor I.M. Govil, who was the first PhD student of Professor Hunt. He was the former chairman of Department of Physics. So, sir, please.
Professor Mahanti,
Professor Gova,
Professor Tripathi, friends, it is really my pleasure to be here on the celebrations of memorial celebrations of Professor Hunt. As already you know, probably I have the longest association with Professor Hunt. I started as a PhD student of Professor Hunt in Aligarh Muslim University in 1960 when Professor P.S. Gill was the chairman of that department. Professor Hunt left for USA for a year, after a year, but then I continued my PhD with him and finished it in 1964. In 1965, I joined Kurukshetra University, and in February, and Professor Hunt, why I joined Kurukshetra University, I was not very much interested to join Kurukshetra University because I was more interested in Aligarh Muslim University. They offered me the post of lecturership at that time. But Professor Hunt wrote me from USA that he is joining Kurukshetra University very soon. So therefore I made the decision that I will not join Aligarh Muslim University, I will join Kurukshetra University. Professor Suraj Bhan was the Vice Chancellor at that time. So he in fact appointed me earlier, but then I declined. But then I told him that I want to come. Then he revived my lecturership, and I joined it. Later, Professor Hans also joined. In '66, Professor Hans decided that we have to get the cyclotron from Rochester University. It was new to me, but he said that we have to do it. But as a lieutenant, I said, okay, if you have decided, then we will do it. So both of us went to Rochester University, dismantled the cyclotron. Why they wanted to offer cyclotron to us was, but they got a better machine, 12 UD pelletron. So therefore, the cyclotron they offered to us, and then we dismantled the whole machine and packed in 6 very big crates and transferred it to India. When the crate came, I am just telling you, as P.K. Halviali said, that how much difficult it was at that time to think of a machine in a university system at that time. So first thing which we came, or hurdle I should say, at Bombay when I went basically to clear the machine from the customs. Customs people thought that we are smuggling gold. So they will just see each and everything, that why you are bringing, why this is, what is this thing, and you cannot explain each and everything to them because they are not scientists. But finally, you are able to convince them, and they cleared the machine. The machine came in crates to Kurukshetra University, and you will wonder that there was no enough place where to put those crates. So there was only one place in Kurukshetra University, and that was the cement store. So we put the whole crates, 6 big crates, in the cement store. Really a remarkable story. In '67, Professor Hans discussed with me what to do, how to open and install. And yes, we have brought it, then we have to do it. But then, in the meantime, Suraj Bhan, the Vice Chancellor, came to Chandigarh University, and he offered Professor Hans the professorship of Physics Department of Punjab University. So Professor Hans came. I left. I was at Kurukshetra. But then the Vice Chancellor there asked me that you install the machine. But I was with Dr. Hans. Dr. Hans said that no, we will do it at Kurukshetra, not at Kurukshetra now, but at Punjab University. The file went to the Chief Minister. Bansi Lal was the Chief Minister, whether we should allow this machine to go to Chandigarh or not. He called me personally, whether you can do it or not. Because I can do it, but the Kurukshetra is not a place with so many resources. It was a village at that time, and to install a machine is a difficult situation. So I explained to him, and he finally agreed to transfer the machine from Kurukshetra to Chandigarh. Okay, so the machine came. I am telling you some of the interesting things, you see, which happened, that at that time, when the machine came and we opened the crate in the physics department in one of the laboratories, how to install it. Nobody knew what is the meaning of vacuum at that time in the department. Nobody knew even the spellings of the vacuum, what to say of the vacuum. In such a large system, to create a vacuum of that order of 10 power minus 6 or 10 power minus 7 was not an easy joke and all that. But anyhow, we had to do it, so we started doing it, putting diffusion pumps and seeing how much we can get it. By the help of whom? With the help of lab attendants who were available to us, or only one person was there who was BSc Bahadur, and most of these people, other people were lab attendants who were looking the lab, as you know what they do in the lab, just issue the instruments and nothing else. So their knowledge was just zero about the machine. But anyhow, there was a sort of a thing, and everybody in the department wanted to say in the university that you have brought the white elephant, it will never work. That was the sort of it. Well, it was a challenge. So we started doing it, and we also got some money for a new building, and we got this building which you see today in the basement. Now the question was how to shift a 20-ton magnet into the new building. The magnet was 20 tons. There was no cranes available of that type here. You can do that. So then we have to reach the Bhakla Nangal, and from their management we got the cranes to pick up the magnet of that order and put at a proper place and all that. And then of course there is a long story about the other other things, the DC generators and all these things. We took help of the Punjab Engineering College engineers. Also we took help of the CSIO which was there in Chandigarh, and finally we were able to make it work. And when Dr. Ramanna came to inaugurate it, he said, I am really happy that you have done it. He just put a sort of a appreciation, hand of appreciation on our soldiers and said that you have made it. So we got the beam, and some of the people at that time also commented, oh, Dr. Govil has shown Dr. Ramanna this beam, not the beam but a torch. That was a sort of a comment the people were saying at that time. But anyhow, people make all sorts of comments, but we focused on our work. But then the next step was, we have got the machine, and as earlier said, that for 10 years we took to get the machine into the working order without any publication, because nobody get the publication for this purpose. So it was a big thing, and you don't get the promotion on the basis that you have put a machine into working. But anyhow, that was the challenge, so we did it. Now the question was how to make use of the machine, because that is important. Nobody appreciates you have got the machine, but what you have produced of it. So we got two research scholars, one was Avasthi and another was Mittal, who started working, and we did the gamma spectroscopy with the first, or very on the because the energy was not very high, so therefore we worked on the light weight nuclei so that we can reach the Coulomb barrier, and got very good results. We got very good gamma rays and published in Physical Review. Most of the papers were published in Physical Review. These two people got their PhD, and then later on lot of the other people also joined this, and they got also the PhD, and total number of PhD produced with this cyclotron was 20 number. Now, because the machine was to be used, and this gamma spectroscopy cannot go very good, because we got this Peletron at Nuclear Science Center, New Delhi. Of course, I will tell you a little bit of the story of that also, as Earlier has mentioned. The Peletron which we got at the Nuclear Science Center was basically meant, he is right, was meant for Chandigarh. But this was in 1990. And when we used to go to UGC for the grant, UGC used to say, I remember very well, why we have money only for this? Your physics, we have so many subjects we have to support, not only physics, and that to nuclear physics only. Well, but finally I should thank Dr. Rais Ahmed came as the Vice Chairman of the University Grants Commission. He helped us and he took it and he talked to Indira Gandhi, and he's right that Indira Gandhi signed the papers, final paper, and the next day she was assassinated. So anyhow, this file was clear, and what you see, the Nuclear Science Center today was the effort of Dr. Hans, and we of course as a lieutenant did our work to get the machine. And it was there that we will get the machine in Chandigarh, but then there was a problem of the Vice Chancellor. The Vice Chancellor at that time was the chemistry man, Professor R.C. Pal. He was not very happy that a machine should come to the physics department, let me say very well. These are some of the things which are there always. So therefore, Professor Srivastav, who was the Vice Chancellor of JNU at that time, he said, all right, I will take up the machine and do it. And the machine was installed at JNU. And the machine was installed, and we saw to it that it has all the equipment of international standard. So all the papers which are published there, they are of international standard, and the laboratory, all the detectors are of that order that nobody can say that our work is inferior to anyone on an international level. So after that, the gamma ray work was gone to the Nuclear Science Center. What we do with this machine, which we are there. Then we thought we have a very good proton beam of 5 MeV, and that is very good for the PIXI work, proton induced X-ray analysis. That is the experiment which was very popular, and it is used for the non-destructive analysis of the trace element. So we started working on that, and you will wonder that we have set up the PIXI equipment here, which is the best in the world, with the least background of the iron. Otherwise, most of the people who have set up the experiments, they have a lot of background of the iron coming from the chamber side. But we have so set it up that it has very minimum background, and the people have done. So there are a lot of 2 or 3 who has got PhDs, and still I think this machine is being used for the PhD using this PIXI setup by the people here. So what I would say is that Professor Hans has a vision always to think big, which we cannot even think, but he has that sort of a thinking where he can think that yes, we can do it and we should do it. So in that way we got the cyclotron, the first cyclotron in the university system. No accelerator in the university system was there, you see, even today. So therefore that was the thing which he imagined, and we got it. And then also the pelletron which we got at NSC New Delhi, we got 15 UD pelletron, while TIFR was having 14 UD at rent. So we thought we should have 1 MeV more than the 14 UD. That's why we got 15 UD pelletron at JNU, so that the university people should not have any thinking that they are inferior or they are not having facilities of lower kind. So that way, you see, that was the imagination and thinking of Professor Hans. We also thought to get it as machine here, but because of certain reasons we could not achieve it. But there is no end to it. One can always try and get it. This is the thing. And now I should say that in the atomic energy always helped us in getting the isotopes. Also the atomic energy helped us in wedges, because whenever there is a radiation, you cannot work without wedges. So we got the wedges from the atomic energy. Every worker who will go into the cyclotron will wear a wedge, and then after 1 month we will send these batch back to the atomic energy, and they will report us. And very many times, at least 2 or 3 times I remember, where they said, stop working, too much radiation you have got, and we have to stop. Like that, you see, also Dr. Mahanti said that we can make the fluorine 19, oxygen 18, and the proton, we have a lot of protons with us, so we can make fluorine 19, which can be used by the medical people, and lot of other things which we can do. The idea is that there should be bill, there is a way. Anyhow, thank you very much for everyone, because
Thank you, sir. We have among us another PhD student of Professor Hans, Professor K.P. Singh. So now I invite him to please come and share a few thoughts.
Professor Mohanty, Professor Grover, Professor Sapati, ladies and gentlemen. Yes, I can say कि मैं हिंदी में बोलूँगा, I will speak in Hindi. हिंदी में जो एक्सप्रेशन आता है वो अंग्रेजी में नहीं आ सकता. साइक्लोट्रॉन से मैं पहला स्टूडेंट डॉक्टर हंस का ऐसा था जिसने कूलम्ब एक्साइटेशन पर पीएचडी किया. 3 साल तक तो मुझे सिर्फ साइक्लोट्रॉन डेवलपमेंट के लिए लगाया, कोई तकलीफ नहीं. आजकल तो स्टूडेंट 3 साल में पीएचडी सबमिट करना चाहते हैं, बट मैंने 8 साल लिए टोटल. और जो कूलम्ब एक्साइटेशन विद प्रोटॉन वाज दी प्रॉब्लम फॉर मी, जिस पर किसी ने काम ही नहीं किया था, न इंडिया में किया था न इस डिपार्टमेंट में किया था. मेरे लिए एक चैलेंज था, हाउ टू प्रोसीड, हाउ टू कंप्लीट पीएचडी ऑन प्रोटॉन कूलम्ब एक्साइटेशन. समहाउ डॉक्टर हंस ये कहते थे नहीं हो जाएगा हो जाएगा. वो कभी जो है ना कुछ नहीं कहते थे, ये कहते नहीं हो जाएगा, करिए करिए करिए. वो हो गया. लोगों की मदद ली, सीखा, सब कुछ किया, एक्सपेरिमेंट किए और अच्छे अच्छे पब्लिकेशन भी हुए. मुझे याद है मेरा पहला पेपर था कूलम्ब एक्साइटेशन ऑफ कैडमियम आइसोटोप्स विद प्रोटॉन. काफ़ी टाइम लगाया डॉक्टर हंस के साथ में मैंने, और वो फिजिकल रिव्यू को उन्होंने भेज दिया और वो बगैर कमेंट के पब्लिश हो गया. ही वॉज सो हैप्पी. उसके बाद जितने भी पेपर लिखे गए हमेशा कहते थे फिजिकल रिव्यू को भेजना, फिजिकल रिव्यू को भेजना. तो उनका ये था कि वो मेरे को इंस्पायर करते थे कि हो जाएगा, कुछ भी करिए हो जाता है, और ये फैक्ट है. अगर आप दिल से कोई काम करेंगे तो होगा. मेरा जो इंटरेक्शन प्रोफेसर हंस के साथ था वो इस तरह का था जैसे ना कि घर में फादर होता है और सन होता है. उन्होंने मुझे टिल माय रिटायरमेंट एज ए प्रोफेसर मुझे ऐसे ही ट्रीट किया जैसे कि मैं रिसर्च स्कॉलर हूँ, और मुझे कोई आपत्ति नहीं थी. मुझे खुशी होती थी कि अपनापन था उन बातों में. इन बातों में अपनापन होता है कि भाई मेरा टीचर मुझे अभी वही प्यार दे रहा है जो मुझे पहले दिया था. आप कुछ भी हो सकते हैं बड़े, लेकिन बड़े तो वो होते हैं जो छोटों को प्यार देते हैं. तो मेरा एक्सपीरियंस बहुत अच्छा रहा. मेरा कंट्रीब्यूशन उनके साथ में बहुत कुछ था. कंट्रीब्यूशन इन द सेंस उन्होंने जब भी मेरे को कुछ भी कहा करने को, मैंने कभी मना नहीं किया. यहाँ IUAC न्यू दिल्ली की बात भी हुई है, उसमें मेरा भी थोड़ा कंट्रीब्यूशन ये रहा कि प्रोफेसर हंस हाथ से लिखते थे एकेडमिक जो प्रोजेक्ट था और मुझे देते थे कि इसको टाइप करा के लाइए. मैं टाइप करा के लाता था, उनको दिखाता था, उसे चेक करते थे, कोई करेक्शन होता था, फिर दोबारा कराइए. इस तरीके से फाइल बन गई पूरी प्रपोजल की. और फिर अब बहुत सारी कॉपी बनानी होती, कैसे बनाया जाए. पहले फोटोस्टैट तो था नहीं, तो टक 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 करके बना दीजिए. स्टेंसिल्स काटे जाते थे पहले, वो मैंने कटवाए हाथों से, सारे डायग्राम बनाए जो बना सकता था. फिर वो सारी कॉपियां बनी. तो मैंने भी थोड़ा सा ये एज ए असिस्टेंट उनका काम किया था. जब तक वो उनके लास्ट डेज थे यहाँ पर, वो जब भी मेरे को कहते थे मैं हमेशा उनके रूम में जाता था, कभी वो मेरे कमरे में नहीं आए, मैं ही उनके कमरे में जाता था, जो भी उन्होंने कहना होता था मैं वो पूरा करने की कोशिश करता था। ये बहुत सारी बातें हैं, वो गुस्सा कभी होते नहीं थे, और एक बार हो भी गए थे, लेकिन उन्होंने 5 मिनट में गुस्सा खत्म करके मेरे कंधे पे हाथ रख करके कहा आंसर, मेरे को गुस्सा आ गया, हालांकि उनको आता नहीं था और पता नहीं कैसे आ गया। तो काइंड हार्टेड थे बहुत ज़्यादा, कभी किसी के बारे में कुछ नहीं बोलना नेगेटिव, हमेशा पॉजिटिव कि वो अच्छा काम कर रहा है, वो भी अच्छा काम कर रहा है। तो इस तरह का आदमी, इंसान हमेशा याद किया जाता है जो हमेशा पॉजिटिव रहता है। तो मैं उनको प्रणाम करता हूँ और भगवान से प्रार्थना करता हूँ कि वो जहाँ भी हैं ईश्वर उनको सब कुछ प्रदान करे। नमस्ते।
Sir, now coming towards the end, I request Professor Ashok Kumar to please come and say a vote of thanks.
Dr. Mohanty, Dr. Tripathi, Professor Grover, Professor I. M. Govil, esteemed colleagues and guests and students. Actually, I belong to the third generation. I am the student of Professor Govil and Professor Jansi, and they are the student of Professor Hans. So when Professor Hans had the room in the cyclotron on the first floor, or ground floor, and at that time, actually 4 academic generation used to sit in the cyclotron. So one day I called, Professor Hans called me in his room, and he told me that I have some data on neutron scattering, 14.8 MeV, and I want to publish it, but I need some calculations. So he asked me that would you do the calculations? So first I was just little bit hesitate, then I told him that okay, I will do the calculations. It is in the, I think, early 2013. So we started the calculations. I think during that period I had lot of interaction, I think, with Professor Hans. I came in this department in '88, but I think during that year I had the most interaction, deep interaction with Professor Hans. And when he was alive, that paper was actually accepted in Physical Review C. but unfortunately that paper was published in the journal after his death. So, but he was very